Hi, I have 20 examples for Math 3 final exam review. We're going to go over different topics, graphing quadratic functions, using imaginary numbers and complex numbers, the conjugate, square root property, completing the square, the vertex form, the quadratic formula, and the discriminant, and also solve by factoring. Let's get started. Number 1. Graphing quadratic functions in standard form. We have y equals 2x to the second minus 12x plus 16. Here we have a equals 2, b equals negative 12, and c equals 16. When a equals 2, which is positive, the graph is going to open up, and c equals 16, which is the y-intercept. The axis of symmetry is x equals minus b over 2a, and that is the opposite of b, and b is negative 12 over twice a, and a is 2. That will give me positive 12 over 4, which is 3. So the axis of symmetry is at x equals 3, which is right here. That is the axis of symmetry. That's going to be also the x coordinate of the vertex. We don't know the vertex if it's going to be below the x-axis, on the x-axis, or above. So let's find the y-coordinate. The y-coordinate will be f of 3, which is 2 times 3 to the second minus 12 times 3 plus 16. That is equal to 9 times 2, which is 18, minus 36 plus 16, and that will give me negative 2. So 3 and negative 2 is my vertex. That's my vertex, which is 3 and negative 2. If you plug in 2, I will get 0. 2 will give me the 0. And 4 will give me 0 because of symmetry also. The graph should look like this. Now we can't reach the y-intercept unless if I zoom out, but the y-intercept will be all the way up at 16. For the domain, quadratic equations or functions, they have a parabola shape, which is going to be all real numbers from negative infinity to positive infinity. Notice that the range is starting from this point all the way up, and that will give me from negative 2 to positive infinity. That's number 1. Let's go to number 2. We're going to be using the square root of negative 1 equals I, the imaginary number. Square root of negative 162. First, we take 162 and we try to factor it. And we end up dividing by 2 equals 81. Now 81 is a perfect square. We don't have to factor it to 9 times 9. There is no need. This becomes square root of negative 1 times square root of 81 times square root of 2. The first part is I, second part is 9, and the last part is irrational, so we keep it. To simplify it, we could write I at the end. So we have square root, or 9 square root of 2 times I. And that should do it. That's number 2. Number 3. We have 2 square roots, but the square root of -1 equals I. So we could do the following. Now 30 is 2 times 15, and neither 15 nor 2 is a perfect square, so let's keep it 30. That will equal to square root of -1 times square root of 30 times square root of -1 again from the square root of -25 times square root of 25. This is an I, square root of 30 times another I times 5. So we end up with 5 square root of 30 times I to the second. And from here we could say that if we square both sides, we get I square equals -1. So we'll use -1 for I square. So the final answer is -5 square root of 30. That should do it for number 3. Let's go to number 4. Since we're not factoring here, we're using the square root of -1 equals I. And we're going to be using the square root property. The square root property states that if you have x squared equals a number, we could square both sides, but make sure you write plus minus. And that is the square root property. So, going back to the problem, we could subtract 36 from both sides. And that will give me x to the second equals -36. Now let's apply the square root property. We have x to the second equals -36, square root of the left side, square root of the right side, and don't forget the plus minus. Left hand side is x by itself, right hand side is plus minus square root of -1 square root of 36. Square root of 36 is 6. Square root of -1 is I. So the answer is x equal plus minus 6i. And that should do it. Number 5. For number 5, I'm taking the time to show you how to find I to the power 399. To do it, let's start with I by itself, which is defined to be the square root of -1. I to the second will be I times I, which is square root of -1 times square root of -1, which is square root of -1 square, and that will give me -1. I to the third, we could, instead of writing I times I times I, we could take advantage of I square, which is -1, and write it's I square times one more I. I square was discovered to be -1 times I, and that will give me a -I. I to the 4 is I times I times I times I, but let's take advantage also one more time of I to the second. So we write I to the second times I to the second, which is a negative 1 times another negative 1, and that will give me a positive 1. Let's summarize it in short so I could add more notes. This is what we have. So we'll keep I, instead of writing it as square root of negative 1, just I. So we have I, negative 1, negative I, and 1. In short, without the steps in between, we have the following. We have I equals square root of negative 1, I to the second equals negative 1, I to the third is negative I, and I to the fourth is 1. How about I to the fifth? I to the fifth will be one more I after I to the 4. So it's 1 times I, because I to the 4 is 1. Notice that I to the fifth is I, takes me back right here. Moving on, we have I to the fifth equals I to the sixth equals negative 1, I to the seventh equals negative I, and I to the 8th equals I. As you can see, it's a pattern that repeats every 4. So from here we could see that I to the 4 is 1, I to the 4 is 1, I to the 8 is 1, I to the 12 is 1. So multiples of 4 will end up 1 all the time. That means I to the 16 is 1, I to the 20 is 1, since it's a multiple of 4, I to the 400 is 1. That means I could go from I to the 4, which is 1, backwards and fill this in, just like what we know for the first 4. So the final answer should be coming from I to the 399 should equal to minus I. And that's the answer for this problem. Minus I, just knowing that it's 1 less than 400, and I to the 400 is 1. Number 6. To simplify this, we're going to use the fact that I to the second equals square root of negative 1 to the second, which is negative 1. So we have I to the second equals negative 1. To rationalize the denominator and end up with the I to be a number, or get rid of the I from the denominator, we multiply both sides, top and bottom, by I. To be clear, we have to put this inside parentheses to show that it's multiplied by both 5 and negative 3i. Let's do this down here too. Now, on the bottom side, it's gonna end up 2 times I, which is 2 times I squared. And let's move on down here. Using the distributive on top, I will have five times I, because we're using the distributive, as I mentioned. 5 times I minus 3 times I squared times I again, which is 3i to the second. Down, it's 2 times I to the second equals 5i. Let's go back. 5i minus 3 multiplied by negative 1, just because I squared is negative 1, and 2 times I squared, which is 2 times also negative 1. To simplify this, we have 5i plus 3 over negative 2. We could break it down and write it as 3 over 2. That's a real part. With the minus, instead of writing the minus in the denominator, we could just part it up or in the front. Negative 3 over 2 plus 5i over negative 2, which is minus 5 over 2i. Notice that both becomes negative because I'm dividing both 5i by negative number and 3 by negative number, so we do have two negative numbers, the real part and the imaginary part. That's number 6. Number 7. This case, it doesn't work to multiply by I because 3 becomes 3i. We need to get rid of the I, and the right way is using the conjugate. The conjugate of a plus bi is a minus bi. You will just multiply by the conjugate, and that is the conjugate. And if you multiply and take your time using distributive property, or the box method, or the FOIL method, you end up with a square plus b square, which is pure. It doesn't have any i's. So we will multiply the top side and the bottom side by the conjugate of the denominator, which is 3 minus i, 3 minus I. That will give me, here we'll use the distributive, and down we use the property stated on the right side. So I have 5 times 3 minus 5 times I, using the distributive on top. Bottom side will be a square plus b square, and that is my a, 3, and b is 1, because it's 3 plus 1i. b is 1. Simplify. I have 15 minus 5i over 3 square, which is 9, plus 1 square, which is 1. 9 plus 1 is 10. Using the distributive property, we have 15 over 10 minus 5 over 10i, which reduces to divide by 5 everywhere. We have 3 over 2 minus 1/2 I. And that's number 7. Number 8. To find the values of x and y that makes the equation true, we need to compare the real part to the real part and the imaginary part to the imaginary part. Let me color things to show you what do I mean by the real part and the imaginary part. The real part now is written in red, and the imaginary part is written in light blue. We will be using the following concept. If a plus bi equals c plus di, a has to equal c, if and only if. A has to equal c and b has to equal d. In our case, we have the following. We have x plus 8 should equal to 3. We subtract 8 from both sides, and we end up with x equal -5. That's for x. For the light blue or the imaginary part, we have 9y equals -18, and we need to divide both sides by 9 to leave y alone, and that will give me y equal negative 18 over 9, which is negative 2. So x equals negative 5 and y equals negative 2. Number 9. To multiply two complex numbers, I prefer the box method, but you could use distributive or FOIL method. And also keep in mind that I square will end up negative 1. So we have 2 plus 4i on one side, 2 and 4i on one side, 5 and negative 3i on the other side. Multiplying for the first box or the first square, 2 times 5 will have a size or a value of 10. 2 times 5. The second one to the right of it, 5 times 4i will be 20i. And down to the left, 2 times negative 3i will be negative 6i. The last one is 4i times negative 3i. Let's take our time to show the steps. That is negative 3i times 4i, which is negative 3 times 4, negative 12. I times I will be I square, but I square is negative 1. Negative 1 times negative 12 is positive 12. Now we need to combine like terms. This is real part, doesn't have i's. This is real part. 10 and 12 equals 22. And combining, let's say 20i and minus 6i is 14i. That is 14i. So the answer is 22 plus 14i. Number 10. Halfway. To solve by factoring, we're not gonna move the 2 to the right side and use the square root property. We need to use factoring techniques. Here's one idea that we need to keep in mind. The difference between two squares, which is a squared minus b squared, will give you a plus b times a minus b. So let's use that. To get to that part and use it, I'm going to subtract 51 from both sides. When factoring, we usually end up with one side, and the other side, the right side, is 0. So this simplifies to x to the second minus 49 equals 0. To apply the method of difference between two squares, I need to see them as two squares with a difference. So we could write this as x to the second minus 7 to the second. So in this case, a is x and b is 7. That will go x plus 7, like a plus b, and a minus b will look like x minus 7, equals 0. Using the principle of zero products, we could say that this gives me x plus 7 equals 0, or x minus 7 equals 0. Add 7 to both sides in this case and subtract 7 from both sides on the left. That will cancel, and that will cancel. I will have x equals negative 7, and I will have x equals 7, and that should do it. Number 11. In this case, it's not difference between two squares because I do have a plus. So we will use the conjugate concept, which is right here. First, let's look at it and apply that it should look like, or it looks like a square plus b square. That is x to the second plus 6 to the second. Now it looks like a squared plus b squared. So on the left side, it's going to be a plus pi. In our case, it will be 6, or x plus 6i multiplied by 6 minus 6i. Again, with the principle of zero product, we will have x plus 6i equals 0, or x minus 6i equals 0. On the left side, subtract 6i from both sides. And here we're going to be adding 6i to both sides. That will give me x equals minus 6i. That's the first answer. Second one, that is x equals positive 6i. And that should do it. Number 12. To factor this and use the principle of zero product, a times b equals 0 implies that either a is 0 or b is 0. We have the following. So we want to make sure, let's start with 3x and x. I don't have too many options for 3x squared. It should go like 3x times x. For 2, I could go 2 times 1 or 1 times 2. I want to keep in mind that the in part and the out will add up to what I want. And what I want is positive 1x. That should be positive 1x. So I'm thinking ahead. That should be 1x. To do it, you could try 1 and 2, but that's not going to work because 2 is going to meet the 3x and make it 6. And the right way is 2 here and 1 here. Notice that 2 times x is 2x and 1 times 3x is 3x. I postponed the negative sign because one of them is going to be negative, either the 2 or the 1, to end up with a negative 2 when you multiply the last part. Since I want a positive x, I need the 3x to be positive, not the 2x. So 3x times 1, that will give me a positive here. Let's use a different color. And that will give me negative. So that's a negative 2x, negative 2 times x. And positive 3x times positive 1 will give me a positive 3x. That will add up to 1x as needed. With the principle of zero product, that implies that we have 3x minus 2 equals 0, or x plus 1 equals 0. We could add 2 to both sides. In this case, we have 3x equals 2. Then we could divide by 3, and that will give me x equal 2/3. That's one option. Let's call it x1. Second option, we will subtract 1 from both sides, and we'll end up with x by itself, x equals negative 1. Let's call it x2. Two answers, solving by factoring. Number 13. Solve by factoring again using the principle of zero products. Let's move the 2x to the left to make it equal 0 on the right side and factor. So by moving 2x to the left, meaning I need to subtract 2x, subtract 2x. And if I do that, I end up on the left with 10x to the second minus 5x equals 0. That's canceling this. Now this factoring technique is different than the one before. We have a common factor, or the greatest common factor, between 10x to the second and minus 5x. I could take 5 and 1x outside from both. 5x times 2x will take me back to 10x to the second, and 5x times -1 will take me back to minus 5x. With the principle of zero product, that implies either 5x equals 0 or 2x minus 1 equals 0. For the first one, divide by 5, or use mental math. I will have x equals 0. Let's call it x1. For the second one, let's add 1. Now I have 2x equals 1. Divide by 2. I have x equals 1/2. Let's call it x2. That should do it for number 13. Number 14. Solve by factoring. So we will end up with, just like last time, 3x times x will give me 3x squared. For 6, I have options: 1 times 6, or 6 times 1, or 2 times 3, or 3 times 2. But before I move on, I need to keep in mind that the inner part and the outer part will add up to what I want. And what I want is -11x. That should add up to -11x. So the right numbers should go 2 here and 3 here without the negative sign. I usually postpone the negative sign till the end. 2 times x is 2x, and 3x times 3 is 9x. Notice from 9x and 2x, I could make -11x by forcing both to be negative. -2x and -9x is -11x, and that's what I want. So I go back here and write negative here and negative here. Notice that -2 times -3 is +6. With the principle of zero product, this implies that 3x minus 2 equals 0, or x minus 3 equals 0. Add 2 to both sides. I will have 3x equals 2. Divide by 3, to leave x alone. That will give me x equals 2 over 3. Let's call it x1. That is my first answer. Second one. Let's add 3 to both sides, and that will give me x equals 3. Let's call it x2. Those are the two answers, 2/3 and 3. Number 15, solved by factoring. We're going to be using the perfect square trinomial. A minus b to the second is a to the second minus 2ab plus b to the second. If you attempt to factor it, it's going to end up with one root, which is just one set, a minus b to the second. To do it, let's move the minus 16 to the right side. Take 2. Number 15. Solve by factoring. Let's move the minus 16 to the left side so we could factor. So if we add 16 to both sides, on the right side it cancels, and that's what we want. On the left side, make sure that you don't combine minus 24x and 16 because they're not alike. The minus 24x has an x in it, and the 16 does not have an x, it's a constant. Sometimes students, they add them up because they're lined up. They think that they have to add them up. We have 9x to the second minus 24x plus 16. We can't combine these two terms. These two terms cannot be combined. They're not alike. Because they're lined up, sometimes students do add them up. So make sure that they don't get added up. Now, the left-hand side is actually a perfect square trinomial concept, which is if you have a squared minus 2ab plus b squared, that will give you the same as a minus b to the second. That's what I mean by perfect square trinomial. That's one form. So this right here goes down to 4, and 9x squared goes down to 3x. And that's what we have. With the principle of zero product, that implies 3x minus 4 equals 0. We could add 4 to both sides. And we end up with 3x equals 4. Divide by 3, divide by 3. And that will give me x equal 4/3. And that should do it. Of course, if you attempt to factor it, you're going to end up with the same thing. And this is what I mean. So if you have 9x to the second minus 24x plus 16 equals 0, and you want to factor it, we need to end up with the sum right here for the in and out to add up to negative 24x, the middle part. And the only way that you could do it is 3x times 3x will give me 9x squared, and 4 times 4 will give me 16. But since I need to end up with the sum of negative, I will go with negative 4 times negative 4. Notice that the inside part is negative 12x, and the outside part, 3x times negative 4, is another negative 12x. So just to support that, you could factor it, but either way, you're going to end up with the same form, 3x minus 4 all to the second. Number 16. Solve by completing the square using the vertex form. Now, to complete the square, we have to follow some steps. We need to focus on the expression x to the second plus bx. Take b, or look at b and take half of it, square that result, and that number becomes the number that will make this expression perfect square. We add it right here, and we'll make it perfect square. The vertex form looks like this: a times x minus h to the second plus k. And to solve for it, I could keep the k, or I could move it to the right side. Let's see what we could do. Here we go. We have x to the second minus 8x plus 10. Let's move the 10. So we could focus on the expression as the note says. The note says we're looking at x to the second plus bx. That's x to the second plus bx. In this case, b is negative 8 b over 2, step number 2, take half of that, which is -4. b over 2 square it. After you take half of b, you square that, which is a positive 16. That is what we need to bring to make it a perfect square. So we could add 16 right here, and that will make it perfect square. However, you can't add 16 and walk away because the equal sign is not going to be valid anymore. So let's subtract 16 to balance it back. So you could always add 16 and subtract 16 from the same side, or add 16 to both sides. I don't want to add 16 to both sides because I'm solving. To solve, I need everything to be on the left. At least for now. And at least to keep the concept of the vertex form clear. Now, we have the following. We have x to the second minus 8x plus 16, x to the second minus 8x plus 16, and we have minus 16 plus 10. That is, let's say, minus 6. These two will make a minus 6 equals 0. The three terms on the left in black, it's a perfect square trinomial, simplifies or factors to x minus 4 to the second. One more time. That is the vertex form. Clearly like a times x minus h to the second plus k. Now to solve, we need to get rid of the minus 6 and move it to the right side. So we have the following. X minus 4 to the second equals positive 6. Let's take the square root of both sides. X minus 4 to the second equals 6. Of course, when you take the square root, the principle of zero products, make sure you write plus minus. Left hand side becomes clearly x minus 4. Right hand side is plus minus square root of 6. Add 4 to both sides. That will give me x equal 4 plus minus square root of 6. If you want to write the answers as separate, we have the following. We have x1 equals 4 plus square root of 6, and we have x2 equals 4 minus square root of 6. And that should do it for number 16. Number 17. Solve by completing the square using the vertex form where a is not equal to 1. Now this right here is when a is not equal to 1. In this case, a equals 3. We need to handle it and make it 1. So let's get started. We need to factor 3 out, and we have x to the second minus, from 24 take 3 out, we will have 8x. We need also, since we are solving, I need to move the 50 to the other side. So basically the focus is on solve, not just write it in vertex form where k is next to it. That's a minus 50. Now, make sure that also you notice that b is -8, is not -24 anymore. So we have b, following the steps on the right, b is -8, and b over 2, half of that, which is -4, b over 2 in step number 3, square it, that's a positive 16. So we need to bring 16 to make it perfect square. The inside part, x squared minus 8x plus 16, is of this type, which is a squared minus 2ab plus b squared. That will give me a minus b to the second. We're using the perfect square trinomial, and that's what we are bringing. we bring 16. In this case, it acts like b squared. This b, not the b that we picked before. So this acts like 16. Now, three times 16, this 3 outside times 16 inside, tells me that I'm not adding 16. I'm adding 48. Make sure that you add 48, or think about adding 48. On the other side, let's add 48. The reason why, if I ask you what we are adding, let's go back and think about the following. X to the second, it looks like it's 1x to the second, but 3 is multiplied by it, so it's 3x to the second, and that is confirmed right here. If I say how many x's do you have, you might say -8, but actually 3 has to be multiplied by it, and 3 times -8x is -24x. So it's misleading if you look at the second line. If I say how many x squares, you say 3x squared. If I say how many x's, you should say -24x. With the same concept, that's not 16. That is 3 times 16, which is 24. So I'm adding 24 to the left. I need to add 48 to the right to keep it balanced. Going back to the problem, I have the following. I have 3 times, and that is what I'm using from the right side, the perfect square trinomial. X to the second comes down to x, and 16 comes down to 4. Of course, we have a minus, so it's a minus. On the right side, -50 plus 48 is -2. Taking the square root of both sides. Before that, let's divide both sides by 3. Get rid of 3. So the left-hand side is x minus 4 to the second, and the right-hand side is -2 over 3. Taking the square root of both sides, we need to make sure that we write plus minus. Left-hand side becomes x minus 4. Right-hand side plus minus. The square root of -1 gives me an I, so I do have square root of 2 over 3 with an I. Adding 4 to both sides, I have x equal 4 plus minus square root of 2/3 I. You could write it as separate. 4 plus and 4 minus would be for x2. But let's keep it this way and say we are done. There are 2 answers, complex solutions. Number 18. To write the function in vertex form, and the vertex form is written down below right here, we then identify the vertex, which is the vertex should be h and k from this part right here, and the axis of symmetry will be x equals h. And if it's a max or min, well, if the graph opens up, we say it's min, and if the graph opens down, we say we do have a max. Let's just first write the vertex form, then we'll come back and fill it in. So we have y equal 5x to the second minus 30x plus 44. We'll write it this way, y equal 5x to the second minus 30x plus 44. Y equal 5. Just like the previous example, a is not equal to 1. I have to factor 5 out. So x to the second minus 5 times 6 will take me back to -30 and plus 44. Now, one more time, like last time, b is -6, is not -30. And that's what we look right here and take half of it. So b is -6. b is negative 6. b over 2, following the steps on the right side, will be negative 6 over 2, which is negative 3. And square that, that will give me 9. So I need to add 9. But make sure, like last time, it's not actually 9. It looks like 9, but it's 9 times 5, which is 45. One more time, we don't have x squared, we have 5x squared. We then have negative 6x, it's negative 6x times 5, and that's negative 30x. So the 9 is not just 9, it's 5 times 9, 45. So we added 45. I need to balance it because I'm working on one side, and write subtract 45 to balance it back. Okay? To make sure that you see it, this is a 5 times 9, which is a 45. That's why I need to subtract 45 from the right side. Y equal 5 times, that's a perfect square, because of a square minus 2ab plus b square will take me to a minus b to the second. X squared comes down to x, and 9 comes down to 3. We have a minus, here's a minus, and square. The outside part of the parentheses is 44 minus 45, which is negative 1. So that is the vertex form. So we write it up here 5 times x minus 3 to the second minus 1. Reading h and k for the vertex, h is 3 and k is negative 1. The axis of symmetry will be x equals h, which is x equals 3. And determine if the vertex is a minimum or maximum. We have a equals 5, which is positive. So the graph opens up. That means we do have a minimum, not a maximum. The vertex is a minimum point, not a maximum point. That should do it for number 18. Number 19. Use the quadratic formula to solve the following. 4x squared plus 2x minus 6 equals 0. On the right side, we could write that a equals 4, b equals 2, and c equals negative 6. Looking for the discriminant, which is b squared minus 4ac. b squared would be 2 squared. 4 times a is 4, times c is negative 6. 2 to the second is 4. Negative 4 times positive 4 times negative 6 is going to end up positive. 4 times 4 is 16, times 6 is 96. 4 and 96 is 100. That is the discriminant. The discriminant is what goes inside the square root right here. That is the discriminant. So we have the 100 that goes inside right here. Now, we write 100, and we start with the opposite of b, minus b. b is 2, over twice a, and a is 4. X equal minus 2 plus minus square root of 100, which is 10, over 2 times 4, which is 8. We have two options, so x1 equal we'll take the plus as an option, and x2 equal we'll take the minus as an option. So minus 2 plus 10 over 8, and minus 2 minus 10, or negative 2 plus minus 10 over 8. First one, negative 2 plus 10 is 8. 8 over 8 is 1. That's my first answer. Second one, negative 2 minus 10 is negative 12 over 8. They both divide by 4. Divide 8 by 4 is 2. Divide negative 12 by 4 is negative 3. So that's negative 3 over 2. That's my second answer. That should do it for number 19. Number 20. Last one. Again, let's find the discriminant first. A is 5. B is negative 30. And C is 45. B squared minus 4AC will be negative 30 squared. That's B, negative 30. Minus 4 times A, 5 times C, which is 45. Doing the math, negative 30 squared, that's going to be positive 900. Negative 4 times 5 times 45 is also 900. So the discriminant is 0. That goes right here. This case we have one answer because the plus minus 0 is going to be out of our way. So the opposite of B, B is negative 30 over twice A, and A is 5. So we have x equal positive 30 plus minus 0, which we don't need to write it down, over 10. So simply is 30 over 10, which is 3. And that should do it.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.